Can you see my screen?
Yes, sir.
Yes, sir. So let us begin and let us continue the discussion from yesterday. And you can ask questions as we go along. Okay. Yesterday I told you that this was an important development in applied mathematics, and also it made a lot of interest, meaning it gave rise to a lot of interest in our own, meaning our understanding of measurements themselves, and in general the question of how to measure things. Okay, and so what the theorem gave was two ideas. Number one was bound on number of measurements. The second is there was also a prescription for how to do the signal recovery. So less measurements is fine. A proof is fine that if you have less measurements, you could recover the signal. But then the second important point is if I actually practically do less measurements, then how do I recover the signal that is of interest to me? And there, the theorem, meaning this article or this paper, also provided a solution, and it suggested a prescription that you can use an optimization with L1 norm penalty. Okay, and so here is a little more explanation on this that I'm going to give you, and I think this is another important point for you to understand why L1 norm gave a good sparse solution. Okay, so the problem that we are interested in is something like this, that you know that or you expect that the function g in that you are trying to recover has a basis expansion or linear expansion in terms of a basis psi n, and this basis is spatially designed, or there are many bases now where for natural signals it is expected that the vector of coefficients beta n will be a sparse vector, which means the number of significant elements in beta n vector is going to be small compared to the total number of elements in the vector. So if your G in was a n pixel image, typically in a linear combination, you will require, meaning formally, if I write a basis expansion, then number of coefficients beta n will be same as the capital N, which is number of pixels in the image. But what we are expecting out of this basis is that the number of significant coefficients will be much smaller. In such a situation, if I actually apply my measurements, what is happening is I'm getting a G out. I have not written noise here, which is included in G out somehow, but the G out is going to be given by this. So it is beta n times the measurement applied to each basis element. Okay, and so for G out, I'm going to get another image or some data. Because G out may be so if M was just some linear combination of pixels, G out will, or like a blurring operation, G out will be an image that looks similar to G in but blurred. But M, if it was a Fourier transform operation, then maybe G out is going to be a little bit different. Okay, G out may not have any appearance that is similar to G in. Okay. But I want to give you a little bit of a geometrical picture. Okay, and so why does so if I pose the problem, for example, this way, that so the problem that I want to pose is something like this, given in equation 75. So I want to look at a cost function, which is now a function of these unknown coefficients beta, such that I have the first term, which is error squared term, but the second term is actually norm of so L1 norm of beta. Okay, and here the L1 norm is defined in this way. So L1 norm of beta is just sum over all coefficients absolute value of beta. Okay, we will come to this little later, but first I want to give you a geometrical picture. Okay. So we are also solving this problem where the number of measurements in G out is actually much less than the number of pixels n. Okay, and so here I'm showing you a picture. So what we are trying to do when we do this kind of problem, equation 75, is that we try to find a minimum of this and find a minimum of this, and then somehow do a trade-off between the two terms. Okay. So suppose I'm going to draw a picture in 2 dimensions, but there are actually n number of axes like this. So I have drawn a picture on beta 1 and beta 2. But since we have n pixels in the image, which could be as large as millions, this picture has to be imagined in n-dimensional space. Okay. So suppose we have a, so forget about the constraint first. But suppose if we solve this problem as a least square problem, where we forget about the second term and we just solve for a problem which minimizes this. Okay, so if you have less measurements than the number of pixels, you will still get some solution, which we have seen before in the IITD logo case and the MRI case and things like that. But the point is you will get some solution, and I'm just saying that this solution may be located somewhere here geometrically. Okay. So beta hat is a solution which is a minimum error solution, and then I'm kind of drawing these surfaces, okay, in n dimensions. So a larger and larger ellipses, for example, represent the contour maps where if you take beta here, it is going to be minimum error. But as you go on to these larger and larger ellipses, the value of error that you will get, if the beta was chosen on one of these ellipses, then the value of the error that you are going to get is a little larger than the minimum error solution. So what we have seen already is here, for example, if you just solve for the first case where first term of the cost function, you get minimum error solution. But if I add this second term, then I'm going to perform little worse in terms of error. But there is going to be a trade-off between error and the penalty term. Okay. So what I want to do is I also want to find a solution which is as shown here as a minimum L1 norm. Okay. And what I'm going to draw here are, so these pictures that I have drawn. So this picture I have drawn is a picture of this a sphere in the L1 norm space. So if I take a equation like this, so how do you define a sphere? In the usual case, I will define a sphere as beta 1 squared plus beta 2 squared is equal to some epsilon squared. Okay, whereas in the L1 space, I will meaning in terms of L1 norm, I will define the sphere as beta n magnitude sum is equal to epsilon. If you look at it, this boundary of this, this figure, which is a diamond-like figure, is going to be the sphere sum of beta n equal to epsilon squared. Okay. So what I want to do is, I want to move away from this point. Okay, and so as I go away from this point, I have increased my error. At the same time, I'm going to, yes.
Sir, here epsilon is the root of the radius, is it?
Yeah, so it is the radius. So for example, in this case, in terms of a square spherical diagram, epsilon will be the radius of the sphere. Okay, in a usual geometry. But in the L1 geometry, if you think about L1 sphere, it is going to be like this, because you want to find a the contour like this, that mod of beta 1 plus mod of beta 2 is equal to epsilon squared. Okay, so this point is, so this point here is epsilon squared. Again, this point here is epsilon squared. But the equation, if I take equation beta 1 squared plus beta 2 squared is equal to epsilon squared, that will be on this boundary of this region. Okay, but if I take an equation mod beta 1 plus mod beta 2 equal to epsilon squared, that will be on the boundary of this diamond shape. Okay, So what I'm saying is, I want to minimize error, and I also want to minimize the penalty term. Okay, so I'm going to start taking larger and larger values of this epsilon, so that this diamond will actually start increasing. Okay, and depending on the choice of alpha I have, I will cut uh, the diamond figure with these ellipses at some point. All right, and that is going to be my solution. Okay, do you get this idea, geometrical idea? So I have to balance two terms, isn't it? I have one term which is error, and second term is alpha times this norm of beta 1. Okay. So what I'm doing is I'm going to take larger and larger values of this L1 norm penalty. So the solution in terms of beta 1, beta 2 lies on the surface of this diamond shape. Okay, and as you move away from this beta hat, you also get a solution which has larger and larger error. As you move away from this, the solution is going to have larger and larger error. Okay. And so wherever these two cut, that is going to be the intersection point is going to be the balance point where the total cost function will have a minimum. Okay. This is just a pictorial diagram, just a simplified version, but it's very difficult to imagine this in three dimensions. You can still imagine, but more than that, it is hard to imagine. Okay, but the idea, yes.
Sir, the blue region is the penalty area.
So blue region is actually meaning the boundary of this is the penalty function essentially. Okay, that so the boundary of this region represents the sphere beta in mod is equal to sum is equal to epsilon squared. So if epsilon squared is increased, this diamond shape will keep increasing like that, the boundary of the region. Okay.
Sir, so if we go beyond if the surface goes beyond beta cap, then will it automatically go to the minimum error solution?
Yeah, meaning now I want to explain this carefully. Okay, so if I keep increasing this, see, let me come to an important point here, that suppose this is my beta hat and this is my surface of L1 sphere. Okay, and somehow I'm going to keep increasing, I'm going to keep going onto these ellipses where the error is more and more, and I'm also going to increase this region. I'm going to grow this region also, depending on what my alpha is. And at some point, they are going to intersect, and that is going to be the place where they're going to intersect is going to be my solution. Okay. But the point is, if you look at this, this L1 sphere is kind of pointy sphere. It is pointy in nature. All right. As a result, when a generic surface like this tries to intersect with this L1 sphere, it is most likely going to intersect at least in 2 dimensions. If you think about it, it will most likely intersect at a vertex of such a sphere. Whereas here, if you think probabilistically, when you grow this region and you grow this circle, you will see that it will intersect at a point which is not at the, meaning there is no vertex here. Everything is equally probable. Okay. But what do I mean? Why I want to bring this is that if you intersect at a vertex, then it is only beta 2 that is non-zero. Beta 1 at this vertex is 0. Okay, so L1 penalty therefore kind of leads to a solution that is sparse in nature. So here in this diagram, when I'm showing you this intersection, this is a point where the solution is sparse because beta 1 is 0 there and beta 2 is non-zero. Whereas if I use this kind of penalty, which is L1, sorry, it's not L1 squared, but it is beta n squared, which is like the L2 norm squared, then it is very likely that you will get a solution that is actually, so this would be like a minimum energy solution. And so that is a solution where, meaning we are not looking at this kind of problems right now, but I'm just drawing this so that there is a comparison in your mind. So L1 solution therefore generically gives you, meaning it gives you a solution that is sparse in nature. Okay. Now look at this a little more carefully. So what happens is if you keep increasing this L1 sphere, what will happen is it will intersect at a point where both beta 1 and beta 2 will be non-zero. Okay. So choice of alpha is very important. If choice of alpha was, meaning if alpha is low, then it means that you don't care about how much is the L1 norm. And so typically L1 norm in that case can grow very large. And so in that sense, the solution, the intersection point will have both beta 1, beta 2 non-zero. But if you keep sufficient alpha, then what happens is you get to a solution point. This contour is a solution point where the error has more value, numerical value, than the minimum error point. But it intersects the L1 sphere it at such a point that typically your solution is sparse. Okay. So this is a very geometrical kind of picture about this. It is not. It may take you some time to imagine this, but this is the best you can do in terms of explaining this. Okay. So the reason why when we use total variation, you see that the gradient became sparse, and so the solution that we obtained had a sparse gradient. And so in the same sense that meaning a lot of pixels had low values of gradient and only a small number of pixels had large gradient. So this is a geometrical picture which has been put forward, and I'm actually putting one article online. I have already put online today, where this discussion is there a little more. Okay, so you can go through it if you get interested in this. But this is just an idea to tell you that TV happened to be a L1 norm penalty, and so that is why it led to a good solution or good penalty for the compressive sensing problem. Is this kind of at least approximately clear?
Yes, sir.
Yeah. So then let's go to the next page. So I'm going to show you how the L1 norm penalty is actually. So if you are doing this problem in some basis like wavelet basis, how is the L1 norm penalty handled? So the problem we are looking at is again C beta is equal to this error plus alpha beta 1. And so L1 norm is defined this way. And again, you will require this functional gradient. And so your matrix now, system matrix is like A, and there is a summation over it. And so, okay, so it should not be N here. Essentially, it will be just a M shy matrix. Okay. And so here M is the measurement matrix, and shy will be a matrix whose columns will be the chians. All right. And so that is how it is. But the important part here is, like the total variation, again, you see that this term has to be handled a little bit carefully. This epsilon is a little bit different than, this epsilon is used for making sure that there is no division by 0. But otherwise, if I write this mod beta n as square root of beta n squared plus epsilon squared, then again, I can differentiate it. And I see that the value of functional gradient, this term, is beta n divided by mod of beta n squared plus epsilon squared. And you see that this quantity is essentially the sign of beta n. Okay, so when you subtract the negative gradient, what you're doing is, if you have positive values, if you have real valued coefficients beta, what you are doing is the positive coefficient you are pushing towards 0 from above, and negative coefficient you are pushing towards 0 from below. Okay. So is this clear to everybody? So this term is important right now, how to handle. All right. And I'm going to show you an example of this, how this works out. So again, forget about this n index here. It is m psi dagger. All right. Okay, so let's move on. I would like to take an example where this sort of thing appears. And the example I'm going to take is from a problem in medical imaging, which is anyway. So anyway, before I go to the problem, here is one more pictorial representation of what we are doing. Okay. Again, this is taken from this tutorial that I have put online. So suppose S is a vector which is sparse, okay, which is like the coefficients beta, and psi is the basis elements, okay. So our image G in is actually psi times this coefficient vector, okay. And then what we are doing is we are having a measurement matrix M, which tries to mix all these different elements, okay. And so this Y is the measurement. And so this is kind of the problem that we have. All right. And this theta is a matrix which is multiplication of M and psi. Okay, so Y is equal to theta times this signal vector, where signal is actually sparse. And since see, the signal vector is 0 at all these places, wherever it is white, the signal vector is 0. Only at these 4 points the signal vector is non-zero, and so only these columns are effectively contributing to the measurement. Okay. Although we don't know a priori, which coefficients of the signal vector are non-zero, because all that we have access to is this Y vector right now. Okay. And so the measurement basis, which is randomized or which is dense. So in general, what you want is that this theta matrix is kind of dense, so that it captures all the coefficients or makes a linear combination of all coefficients of S. Okay. And then what I want to kind of note here is that, well, as per the Candace-Romberg Tau theorem, it is good to have randomized measurements, but unfortunately in all systems, it may not be possible to get. So this is just a note to remember that randomized measurements are ideally required, but they are not always possible. However, the philosophy behind L1 norm and these ideas is still proving to be quite useful in large number of imaging problems. Okay. So this pictorial representation, is it clear to everybody what we are doing? It's just a picture, but this is the problem we are trying to solve essentially. Okay. Is it clear to everyone?
Yes, sir. Yes, sir.
Okay. So let us go ahead. I want to take one simple case where I want to show what happens. Okay, in this case, I'm going to take an example of what is known as Fourier domain optical coherence tomography. Okay, this modality has become very important to do subsurface imaging in biomedical applications. So here there is a example of imaging of retina. So here is, for example, along this line, you can see that meaning as you go in depth dimension inside this surface. Okay, this is a picture of retina, but this is retina as you go inside it. So these are different layers of retina, and actually you can see a large number of layers, which if you send light in, they will reflect light out. Okay, and so generally this modality works in near IR, where the light penetrates a little more inside the skin or tissue. Visible light will scatter away, but so the idea is this modality is essentially a microinterferometer. Okay, and so what is done is you have a broadband source, or there is a swept source sometimes, where you are actually taking the source wavelength over a broadband. Okay, but so you're tuning the source wavelength. But here, for example, this is a, let's say, a broadband source, and here when I say broadband, it is like 50 to 100 nanometers. Okay, so not broadband means not a white light source, but this is how it works. Okay, so suppose I have a broadband source and I send light in a Michelson interferometer, and the sample has many reflective layers. Okay, so this signal comes back, and this signal comes back, and then this signal is actually sent to a diffraction grating, and then it actually the signal is recorded on a 1D detector. So you actually detect a spectral signal. Okay, so how does the signal look like? This signal is a function of k, which is the wave number, and so if you think about this beam, it goes and comes back. So let's suppose that this distance is ZR, which is the reference beam distance. So reference mirror distance from this point. So if you think about this beam that goes, and there is a reflectivity to this mirror, and so it has traveled twice this ZR. So it has gained a phase of e raised to ik, 2ik ZR. And whereas on this side, there is summation of the return signal is essentially summation of reflection from different planes. So you have a reflectivity Rn corresponding to a particular nth plane, and the Zn represents the distance from this point in the center of the setup to a particular layer Zn. Okay, and so there again you have twice traveled this path twice, and so this is a interference pattern. Okay, and what you are doing is, since this is a broadband source, you are actually sending this pattern onto a grating and dispersing it. And so at different points on the detector, you get the interference corresponding to a different k wave number. Okay, so this interference signal on this detector is a function of k, or wavelength. All right. But if you expand this, what you will see is that if you take the two intensity terms, there will be some constant so this actually is done at every location in xy. Okay, so as a function of xy, so there is a signal that is a function of z and k. Okay, but you see that the signal is there is some constant term plus these cross terms. These cross terms are going to be something like this, where there will be a cosine signal, and then there will be terms that are corresponding to the self energy in these terms, or cross terms of this sum itself. So there will be interference between the nth layer and mth layer and things like that. But generally in these problems, the reflectivity is small, and so these second order terms are neglected. So mainly the signal is like a cosine, sum of cosines. Okay. So the signal looks that you get on the spectrometer looks something like this, and then it is a function of k, and so it is also a function of frequency of light. And so after you actually do a processing of the signal, you actually get peaks that are at locations ZR minus Zn, and so you can actually get the peak locations, and the value of the height of these peaks tells you something about the reflectivity. Okay, so and then this image is formed point by point by scanning this source on a sample. So there is a XY scanning, and so at each point XY you get a image along Z. Okay, so this kind of scan along Z is called as A scan image, and then when you scan along the XY dimensions, it is called as B scan image. And so you combine the images at all these locations, and then you get a 3D map of the internal structure. So this kind of imaging cannot go very deep inside the skin, but you can still image up to say half mm or 1 mm. But there is a lot of information in that. For example, if you image retina, a lot of diseases reflect actually things like diabetes, for example, show a lot of changes in internal structure of retina. And so this kind of imaging is performed where you can actually get a signal which is like sum of cosines. Okay. So let us see if we have sum of few cosines, what does the signal look like? Okay, so what I have done is I have taken a vector which is sum of 4 cosines, and this is a vector which is 256 length vector, and it is just sum of 4 different cosines. And what I decided was I'll just choose 50 random measurements. So I have shown some arrows here. Okay, so I'm not going to measure all 256 numbers, but I'm going to just measure at these arrow locations. Okay, and so these 50 measurements give me some signal like that. And so if I try to solve this problem, now you see the thing is my measurement basis is directly picking signals, samples randomly, and my signal is just the sum of few cosines. So in the cosine basis or the discrete cosine transform basis, my signal is actually sparse. So in the pixel basis, it is not sparse, but in the discrete cosine transform basis, the signal is sparse. And so if I take less measurements and if I try to solve this least square problem, then this is what is the solution that I get. Whereas if I add the L1 penalty on the cosine, discrete cosine transform coefficients, then you see that you can get a really nice sparse solution where only these coefficients are non-zero, other coefficients are actually 0. Okay, so this you have to relate back to this equations. So this is the kind of equations I am solving. M is the matrix which actually just samples this signal randomly. Psi are the cosine transform basis vectors, and betas, there are only 4 betas there. And so the solution was able to, meaning see here, instead of 256, I measured only 50 measurements and I still get reasonable solution. Okay. So this is just an illustration of trying to do this L1 norm like problems in meaning instead of using TV, you can also do this in some preferred basis. Okay. Is this clear? Maybe I will give you an exercise sometime later to implement this yourself, and then you will see what I'm doing. But the idea is less measurements are still able to solve this problem. When you put L1 penalty, then you see that you get a sparse solution of transform coefficients. Whereas if you do not use the L1 penalty, you get a minimum error solution, but here a lot of, meaning all coefficients are kind of non-zero, and that does not make any sense because this original signal was just a sum of 4 cosines, and so it should have given you a solution which is sparse. Okay, is that clear?
Yes, sir.
Yes, sir. Okay. So this is again, I'm showing you just a 1D example of doing this in a basis rather than in the image space directly with total variation. Okay. There is another example which was shown when this compressive sensing came along, and it is called as single pixel camera. Okay, and later in the class I will give you some literature, or if we get time we will learn about this ghost imaging as well. but both of them are essentially similar. Okay, so the idea is, sometimes if you operate in wavelength regimes where making detectors is very hard. So suppose you operate in terahertz regime, for example, it is very difficult to make an array detector like a CCD camera, and so one point detector you can make. But if you want to think about a camera now, see, traditionally you could never think about a camera which has only one hardware pixel. Okay, so the idea here is something like this: that I have a scene, and maybe I have a lens, and I project the image onto this device. So this is actually a digital mirror device, for example. This was used for this experiment. And this digital mirror device is actually there in all your projectors. Overhead projectors now have this kind of device. And what this device does is there's an array of micro mirrors, all right? And these mirrors are about 10 micron in size. And what you can do is you can flip these mirrors. Okay, so if this mirror is in right position, it will reflect light. But if the mirror is in flipped position, it will block light. And so these mirrors can be moved individually at a kilohertz rate. And this creates the grayscale. So if a mirror is turning on and off and on and off, for your eye, it will feel, depending on the duty cycle, you will feel that particular pixel that is projected is at a grayscale level. If the mirror is always on, then you will see the brightest, you will see a pixel as brightest. If the mirror is always off, then you will see a dark pixel on the projector. The idea here was, what was done was these patterns of this DMD were actually treated as, as the basis elements. Okay, so what you are doing is the scene is projected onto this, and then you have a pattern like this, which is a DMD pattern. So each of these patterns of 1 zeros you can treat as a basis vector. And so what you do is when you are measuring this image, you are actually measuring some of these pixels where these mirrors are on. Okay, and then this whole thing is integrated by a lens, and it actually integrates this whole pattern onto a single detector. So at a time, what I get is a scalar product of the scene that I want to image and the pattern that I have on the DMD. And since I can do this at a easily few kilohertz rate, what I can do is I can actually display many patterns and DMD one after other. And so on the single pixel detector, I will get a time domain kind of time varying signal. And so this signal was sent out somewhere else, and then depending on what patterns were used, which DMD patterns were used, you can use this into a compressive sensing type algorithm and do image recovery. Okay, so here, for example, this the images that were used had 256 by 256 image, but only 1300 random measurements were actually sufficient to reconstruct the image with this single pixel kind of idea. Do you understand what this single pixel camera is doing?
Hello, sir.
Yes.
Sir, here we are kind of mapping the intensity which we are receiving with different pattern, is it?
Yes. So what you are doing is this scene will be imaged onto this DMD chip. Okay. And on the DMD chip, only some of these mirrors will be on and some mirrors will be off. Okay.
Okay.
And then what you're doing is you're just summing up all of them onto, so light from all the on mirrors will be summed up into
for one pattern.
For one pattern. Okay. So one pattern, what the value that you get in single pixel detector is like a scalar product of this scene with the pattern.
Yes.
Okay. So this is like my measurement vector. So I'm going to I'm projecting the scene onto this. And then I'm just doing a dot product with of the scene with the DMD pattern. Okay.
And
then
you're
this
adding
whole
all
thing
of
is
them.
integrated. Yeah, because I'm just integrating on a single pixel with a condenser kind of lens. Okay.
So you are saying it took only 13,000 different
1300
patterns for
1300
1300.
patterns.
Sorry,
Yeah, so 256
1300
squared.
patterns.
So for example, if
Okay.
you do 256 squared, how much is that?
256. Okay.
That is 65,536. Okay. It's
So,
like yeah. So out of that, only 1300 random patterns were used here. And so 1300 patterns means if my DMD chip can record the image at say 4 kilohertz, 5 kilohertz, then my total time to take this picture was less than a second. And so I have collected this picture, and maybe I can, meaning this is just a show, but I can essentially send these coefficients to somebody else who knows, what patterns were used. And then just from this time domain signal, I can, with the knowledge of the DMD patterns, I can recover the picture. Okay.
Excuse me, sir.
Yes.
Sir, as you said that in the DMD chip, some mirrors will be on and some mirrors will be off.
Yes.
How does it read the image?
No, the image is not read by DMD. Image is reflected by the DMD into the detector.
Okay, sir.
In the projector, what happens is you send a pattern that you want, okay, from behind, from a computer. If you have so in a projector, what happens is there is also a color wheel, and there is the pattern that you are sending. For every pixel, you see what is the gray value. Depending on that, the duty cycle of each mirror is adjusted. And so these mirrors kind of keep flipping on, off, on, off, on, off. And so that within your visual response, you actually see grayscale values. Okay, so this chip is kind of not very expensive now, and you can get it even as a demo kit. Okay, and so, yes.
So, sorry, here, like, all of these patterns must be unique, no?
Yes, all these patterns are unique because the point is if two patterns were same, it will give you the same data, isn't it? Okay. Or you also don't want them to be linear combinations of each other. But you can make such patterns. There are you can generate random patterns which are not linear combinations of each other actually. So linearly independent. So for example, if I have n pixels, n mirrors on the DMD chip, I can always generate n linearly independent vectors, okay, that are made from ones and zeros. See, at the worst, what I can do is keep only one mirror on, okay, at a time. All right. So that will only give me pixel by pixel image formation sequentially, but that is not the best way because I will need all n measurements. Whereas if I do these patterns, then I can actually get the same image approximately by doing much less number of measurements.
So the number of linearly independent patterns will be certainly less than the 256. I mean, all the possible patterns possible.
Yeah.
Okay.
But you see, 256 squared is the image pixel size.
Yeah, not 256. The combinations of it. Sorry.
Yeah. But anyway, this was one of the early demonstrations of what compressive sensing can enable. Because before this, you would never think about a single pixel camera, isn't it? Mm. But with this kind of, because a single pixel camera before would be just a raster scan. Okay, so you will need a galvanometer which will just scan a spot of light on the scene, and then one by one you can collect. For every pixel you can sequentially read out what is the intensity. And so that meaning that is not a very good proposition because hardware wise it is a brutal, it's a kind of a brute force kind of methodology that you have to measure every pixel sequentially. So traditionally, if I told you I have a single pixel camera, you will say, okay, this is not very efficient because I have to scan pixel by pixel. And so I have to scan all the n pixels. But here you see that I'm not really scanning all the pixels, but I'm scanning. So what I'm measuring are these scalar products. And then I see that number of scalar products, which is about 50 times less than number of pixels, is still able to give reasonable picture, not accurate, but maybe it is sufficient for the application I'm doing. Okay. Again, here this much of reduction is possible because this letter R is highly sparse, for example, in the gradient domain. Okay. Otherwise, for a more complex object like this cameraman, this much reduction in may not be possible. Okay. So this again is explained a little more detail in the paper I have. So there is a tutorial article in IEEE Signal Processing magazine on this, and I have put this article for you to take a look at. It's a short article, but it explains, it was in the early days of compressive sensing that people were trying to figure out how this works. And it is at that time this tutorial was written, and it's kind of nice. It explains several advanced concepts that we have been talking about in short 3 or 4 pages, okay, with some pictures. All right. So you can go through that.
Hello, sir.
Yes.
So this image is like GXY, like there is some values of intensity in it, like every
which
point
is
in the
the
image.
scene. GXY is the scene. Okay.
Yeah, and we are taking the dot product, and these mirrors like 0 or 1, we can imagine it like a 0-1 basis, like we do in quantum mechanics. So there is the one mirror that is reflecting, we can take it as a 1, and which is not reflecting as a 0, and we are taking the dot product.
Yes.
So we are getting particular, like we are getting particular pixel values. What is the value in that particular pixel?
You are not getting particular
reason...
pixel values. You are
Okay.
measuring the signal on a single pixel. So you are getting sum of all the on pixels.
Okay. Yeah. That's and that's actually what I mean.
Okay,
so every like whatever the...
Yeah, so you think about this scene and divide it into 256 squared. Okay, this scene falls onto this DMD. Some mirrors are on and many mirrors are off. Okay, and then all of this is integrated onto a single detector. So detector gets a sum. Okay, so it gets the scalar. Okay.
Yes.
But depending on the pattern, the total signal received by the detector will be different. All right. So there will be essentially for every frame, there will be some signal on the single pixel detector. But this is a very simple but interesting example of what computational imaging can do. And it's really now you can think of, you don't have to go extreme. For example, you don't have to go all the way to 1 pixel detector, but you could also think about a camera where, it is only 3 by 3 pixels, for example, and then correspondingly the number of DMD patterns we will have to show will be less, isn't it? Can you see what I'm saying?
Yes, sir.
Suppose instead of a single pixel detector, I put a 3 by 3 detector here. Sometimes there are avalanche photodetector arrays available. Okay, and now this is also interesting when the light levels are a little bit low. Okay, because so suppose this is a night vision kind of scene. Now what happens is, since you are integrating a lot of pixels at a time, you may have some overall signal to noise advantage. Okay, because while you are imaging, you don't care about the resolution so much. You are only looking at 1 pixel, so you are just integrating the total signal. So you could also think about a situation where you have maybe a far off scene, and what you do is you send these patterns as from illumination. So you are sitting with a illumination. So you have capability of sending out illumination patterns, and so you send a lot of illumination patterns out as a remote sensing problem. And then this return light, you don't worry about in a way you don't worry about how distorted it is or whatever, but you just collect the total light with a you know, what is like a condenser kind or telescope or something like that. And so you can operate single pixel camera in this way. So later we will discuss this idea of ghost imaging. You will see that ghost imaging is essentially exactly same, but instead of the DMD patterns, you have generally they use speckles as a random patterns. But otherwise, I think both of them are completely identical. It's just that single pixel camera is known in the electrical engineering community, and the same thing is called as ghost imaging in physics community. Okay, but operationally both of them are identical essentially. And the reconstruction part, for example, is there is no real difference. All right. Okay. So as a summary, yes.
The part you are teaching, like last three lectures, let's just say,
Yes.
is there any reference or anything that we can get more
So
insight about these topics?
three papers. I have already put 3 papers online, which explain the MRI problem, the black hole problem, and this tutorial on compressive sensing. So you can actually go through that. You may not, so the tutorial, you will understand everything almost. Other papers, there are details about the systems themselves, but you can see how the images are reconstructed. At least that part you will understand. Okay.
And I'm talking about the mathematics that you have taught during these lectures.
Mathematics, I can put something online. All right. Meaning,
please, sir, do this.
Yeah. But again, meaning there is not too much material out there that explains the things in the way I am teaching. Actually, I have not really found anything like this, but I will try to find a few resources like that and try to. So the problem is, what is available out there is either too mathematical or has no mathematics at all and only focuses on applications. So, but what I want to teach is in a way that you can, do things operationally. If you read Candace Romberg Tao like papers, then it is impossible to get anything at your level where you can just take something and implement it. But if you take just application papers, they will not explain how it is done. So I'm trying to take a little bit of a middle path where you understand, operationally how things are done, because that is much more important than just showing you some fancy images or fancy applications. Okay, so but anyway, I'll try to still find something that is very much similar to what we are teaching, learning in this class. Okay.
Okay.
Yeah. So this kind of concludes the first part of this course, which is the mathematical methods essentially, and so we or the basic framework. So I discussed initially the basic concepts of Fourier optics, angular spectrum, FFT, diffraction computations, etc. I discussed Wiener filtering. Then we went on to the Euler-Lagrange framework for image reconstruction problems. And I looked at a few problems where like the noise removal problem and the iterative deconvolution problem with TV penalty. And then for last few lectures, we have been discussing this important topic of compressive imaging. So things like why measure less and what this L1 norm-based reconstruction allows you. And the examples I have looked at are the MRI, the Event Horizon Telescope, the single pixel camera, etc. Okay. And so today I will stop, but from the next class, we will actually start discussing the coherent optical imaging part. So how these ideas now can be utilized in coherent imaging or imaging phase of light and things like that, detecting optical wavefronts. And the third part will be going towards incoherent imaging, but we will discuss those two later on. Okay. Again, I have to say this that there is not too much literature which describes the, the content exactly in the way that I taught. It is something that, meaning this is how I understand these topics, and that is how I am teaching this way. I'm really not following any book, but I will try to put some literature anyways for you. Okay. Okay. So we will stop today as we are kind of going over time.
Hello.
Yes.
Sir, what will be the syllabus for minor one exam?
We will keep maybe how many lectures are remaining before minor now? So what I will do is I will not keep everything all the way to the end. Maybe even one lecture before, I can also keep more as a discussion lecture where you can ask as many questions as you want during the class. But I will, we will just start with study of coherent imaging. I will tell you, meaning I will not try to, up to today, definitely everything is included, but maybe one or two lectures later, or what we learn this week, maybe we will keep. But after that, maybe I will, uh, let us see, meaning I will inform you few days before the minor, but till today, whatever I have taught, definitely it is going to be there. Maybe few more lectures. What is will also be there in minor now. Okay, but not all the way to the end. Okay, that I will make sure that we will not go all the way to the end.
Okay, sir.
Okay.
Hello.
Yes.
Sir, the format of the exam will be coding based, right? And we'll have to submit codes.
I don't know, meaning I will have a mixture of things. Maybe I have not yet decided how to do it. There may be some coding that you can submit little later, or but I will try to make questions that are more conceptually oriented. So you can, meaning it may be more of interpretation of what you see in pictures and things like that. So we will have some written part, and a code exercise I can give you a little bit extra time, but I'm sure, generally during the exam, you may have other exams on the same day or the day after or something. So I'll be conscious of that. I will not put too much coding into it right away. But I can
Sir,
still
would
give
you
you problems where coding is involved, meaning I may write a piece of code and try to see if you can interpret it and things like that. Okay. So I will try to make an exam which is a little bit different. Okay.
Sir, but it will be online, not handwritten, right?
We can make it handwritten. That is not a problem, because I think if they give us, like a 1 hour slot or something for the exam, maybe you can quickly write answers and scan them and send it to me back, because that is meaning generally if it's a slot like that, then I don't expect that everybody will be comfortable in coding within 1 hour and not get stuck and things like that. Okay. So the exam could be written where you will be tested for your understanding rather than coding skills right away. I'm giving you coding exercises in homework anyways, so that part is already being tested there. Okay, I can always make up an exam which is a little bit like a normal exam.
So we'll have to solve equations like usual exams.
Yeah, but it will be open book. So, I can't really put right now the way we are handling things. We can't actually, so you can use your notes, you can use my lectures for exam. So it will be more not memory based, but it will be a little bit thinking based. Okay. So you don't have to memorize anything. It will be everything. All the material is available to you, but I will make questions that are more interpretation based or something you can quickly work out within few lines, or let us see. Okay. Because this year the pattern of exam also has to be a little bit different. I can't Because we are doing this remotely, I don't want to do it exactly the way I do normally. But don't worry about it. To try to understand, the more important thing is to understand the material. If you have any questions, you can pose questions. I will keep one class before minor open just for that, where we can discuss everything. You can ask me as many questions. But focus on understanding, in your mind, things should be clear. Then you will be able to answer questions. Okay. ठीक है. All right.
Thank you, sir.
Thank you, sir.
Okay. Bye.